All right, so in the last video, we took a quick look at sort of the mechanism behind double displacement reactions and sort of seeing how ion exchange works. In this particular one, we're going to take a quick look at the solubility rules. How do we know which new combination might be the precipitate? How do we identify which one could be forming this mystery solid that we may potentially see? So again, I kind of had this in that last little video. It's a super cheesy animation, I know, but that idea that you have two original solids, AB and CD, and that when you dissolve them in water, they dissociate into separate ions. And here I have them dissociated now, just about ready to mix around. And then you have two new possible combinations, right, for what they could be. Possible combinations in terms of who comes into contact with who. So compound A here originally started bound up with compound B. That was soluble. They came apart and dissociated. But now they could eventually bump into compound or element D for whatever reason. And I think in this particular video, I have these two are the ones that formed our precipitate. And when they bump into one another, they form a larger molecule. Their intramolecular attraction is relatively large. So they form this new molecule that's a little bit heavier now. And as it's heavier, eventually it is going to start to kind of sink to the bottom. These guys, when they bounce into one another, they're fine hanging out with one another, but they're still not that super attracted to one another. Temporarily, yeah, they'll attract, but then the water molecules will pull them back apart and they will re-dissociate. So they'll come, these guys will avoid one another. Those guys would bounce off one another, be fine, and then bounce apart. These guys would avoid one another, so no way. These guys could avoid one another. Those guys could be attracted to one another. And once they come into contact, they stay in contact and sink out. This little guy up here, we could float around, maybe be attracted, but again, come apart, again, etc. That whenever the purple and the yellow ones here meet one another, they are more attracted. Again, this would be repulsion. This would be the original combination. They're attracted to one another, but not that strongly. That would be repulsion. That would be attraction and strong attraction. So those guys, again, would settle out. So again, just that idea of visualizing all of these ions sort of bumping around into one another. And every once in a while, it's like, oh, hello, cation. You are the most amazing. We need to go discuss, right? We need to go have a little private space and talk to ourselves about what kind of solid we could form together. And they're going to settle down to the bottom of that pool. Those other ions, they're still hanging out there, having a good time. It's a pool party, man. They like what they are doing, bouncing around, floating around. They're good. So how do we tell, right? How do we tell which ones could form that precipitate versus which ones don't form that precipitate, right? They're always forming these new combinations. You may even have some leftovers, right? But they're always forming these new combinations. How do we know which ones are going to form the right combination? Well, this is something called solubility rules. Luckily for you, there's plenty of people who have studied this through the years and have created a short list of rules to sort of predict what the patterns are. There are certain ions that we know form strong intramolecular attractions that once they come into contact, they stay in contact. And there's other ones that we know are pretty much just kind of bro ions, like they're hanging out with everybody. They're always just friends. They come into contact, they reseparate, come into contact, reseparate. Those are what we call soluble. So the three words or three phrases that you need are soluble, insoluble, and slightly soluble are the ones that you need to look at. So the term soluble here, oops, wrong pen. The term soluble here, this means that the ions stay separated. Soluble means separate. That's actually what that means. That the ions are going to go their own way and float through that particular thing. So in other words, the attraction between these ions and the water is the stronger one. Insoluble is the opposite. When these guys come together, they stay stuck together. They are so into each other that they literally are going to settle out to the bottom. That's insoluble. In other words, they form a solid. They do not separate. They do not stay dissolved. Insoluble is your precipitate. So that's actually what you're looking for, PPT. This phrase slightly soluble is a little bit of a messy one that comes to solubility rules. And it really depends if you're talking about microscopic or macroscopic, right? If you're talking about microscopically, slightly soluble means that they come together, but maybe every once in a while they kind of separate, but they like to stay together. For most of the purposes of what we would be doing, when you see the word slightly soluble, that actually also means that it's probably going to form a visible precipitate, but maybe not 100% as much as it could have otherwise. It's going to reduce yield. So again, slightly soluble, generally is the same thing as saying insoluble, right? For the most part, when those guys come together, they stay together, and only a little bit of the ions are going to kind of stay separated. So that's really the idea. Are they more into each other? Insoluble, forming a precipitate. Or are they more attracted to the surrounding water? That means that they are soluble. So like I said, luckily for us, there's actually lists of solubility rules. You can just go Google solubility rules. There's all different kinds of ones. This is very similar to the one that's in your textbook. I added the couple extra little phrases on here to make it exactly like your textbook. Very similar to your textbook. Like I said, there's charts, there's tables, there's graphs, there's all different kinds of ways this is presented. But they do all basically say the same thing. When you have a list of solubility rules, the way that you tell is you apply these rules from the top down. They're always presented in the sort of order of importance. So as soon as you find a rule that applies, you stop there. It is possible to get what looks like two rules that argue with one another that say a different story. So as soon as you see that first rule that applies, you stop at that first rule. So we can take a look at some examples here and kind of see which ones would be soluble or insoluble, whatever they work at. So remember, soluble means you don't see it. If you see insoluble, where would be insoluble? Important exceptions: moderately soluble, slightly soluble, slightly soluble. That means those are going to be forming the precipitates. There's a precipitate there. Moderately soluble, that's a precipitate there. We'll talk about exceptions. Most of them are soluble except for. So we'll take a look at what some of those different ideas mean. Okay. So the way this works, if I want to see if zinc chloride, for example, is a possible precipitate, is that going to be soluble or is that insoluble? I would take a look at my rules here and I apply them from top down. So I go, okay, zinc chloride. Does rule number 1 apply? Well, rule number 1 is about nitrates. Doesn't apply. Rule number 2, most salts of sodium, potassium, and ammonium, basically the alkali metals, the +1 metal family, those are soluble. Yeah, this is zinc. Doesn't apply. Most chloride salts are soluble. Okay, so I have a chloride here. So this tells me this is likely soluble. And then it says, hold on, there are some notable exceptions. Okay, notable exceptions means most chloride salts, including bromide and iodide salts, most of these are soluble except for silver chloride, lead 2 chloride, and this is mercury 1 chloride. It's that polyatomic weird version of mercury. So these 3 right here could form precipitates. In general, chlorides do not. So that means this is probably soluble, not the PPT. Okay, that's not the one that we would see. All right, let's take a look at a couple other examples here, kind of run through how they work. Okay, lead 2 nitrate. Could this be a precipitate? Again, start at the top, work your way down. And I look at rule number 1, most nitrate salts are soluble. Oh, this is a nitrate. Most nitrate salts are soluble. Done. Go no further. Not PPT. It's soluble, right? There we go. There we go. Lead 2 sulfate. Okay, well, we haven't looked at lead 2 sulfate yet. So rule number 1 is nitrate salts. Nope. Rule number 2 is the alkali metals and ammonium. Nope. Rule number 3 is chloride, bromide, iodide. Nope. Rule number 4, sulfate salts. Oh, okay, this is a sulfate, all right? Most sulfate salts are soluble. Okay, so generally sulfates are going to dissolve. Notable exceptions are barium sulfate, lead 2 sulfate, and calcium sulfate. So this is an exception to rule number 4. So this means this is going to be a PPT. That is going to be, and it's actually white. This is definitely going to be one of those cloudy solids that would form. Because it's lead 2, it's an exception to the sulfate rule. All right, sodium iodide. How about that one? Okay, rule number 1, nitrate salts, doesn't apply. Rule number 2, most salts of sodium. Oop, that applies. Most salts of sodium are soluble. Soluble. All right. Nope. Not PPT. That's going to be dissolved or aqueous. All right. Cobalt 3 sulfide. All right. Again, top down. Most nitrate salts, doesn't apply. Salts of sodium, potassium, ammonium, alkali metals, doesn't apply. Chloride salts. Nope, doesn't apply. This is a sulfide. Does not apply. Okay. Most sulfate salts. Ooh, sulfate, sulfide? Nope, not the same thing. Okay, number 5. Most hydroxide compounds are only slightly soluble with some exceptions. Okay, well, this is not a hydroxide. So next rule, rule number 6. Most sulfide, carbonate, Phosphate and chromate salts are only slightly soluble. This is a sulfide. So if it's a sulfide, sulfide salts are only slightly soluble, so only a very small number of them are going to separate. That means this one here is going to be a PPT. Again, that's by rule number 6. Okay, and then our last one, chromium 4 hydroxide. That's what it says behind the little video image there. Sorry, chromium IV4 hydroxide. So again, top down. Okay, rule number 1's nitrates doesn't apply. Rule number 2, sodium potassium doesn't apply. Rule number 3, chloride salts doesn't apply. Rule 4, sulfate salts doesn't apply. Rule 5, hydroxide compounds. Okay, hydroxide compounds are only slightly soluble. Okay, so that could be our precipitate. Important exceptions are sodium hydroxide and potassium hydroxide. Sodium hydroxide and potassium hydroxide are soluble based on rule number 2. That's why those are really important exceptions for us. So barium hydroxide and calcium hydroxide are only moderately soluble. Okay, so chromium 4 hydroxide. Most hydroxide compounds are only slightly soluble. That means this one is only slightly soluble. Therefore, that would be our precipitate. So again, when you find these rules, when you have the solubility rules like this, you always apply them from top down. As soon as you hit a rule that works, you stop at that rule. And again, one of those rules like NaOH is a really good one, that hydroxide rule, right? Sodium salts are soluble. You don't have to go any further. You don't have to go down to the hydroxide rule to say anything else about it. Be done when you get to that first rule that applies. By the way, shortcut rule. This isn't a perfect rule because there's always exceptions, but this is a great shortcut rule. If you just want to take a quick glance at a chemical reaction and say, hey, what do I think might be my precipitate? You can think about the word nacl-noso. Nacl-noso. So nacl-noso are not your precipitates. So if you have anything that's got sodium, chlorine, nitrate, and sulfate, chances are pretty good that it's not your precipitate. There are some important exceptions to this, but these are the not precipitates. Nacl-noso says, yeah, probably not so much. Again, there are some important exceptions. So the important exceptions right here, silver, lead 2, and mercury 1 are the exceptions to the chloride part. Nitrate does not have any exceptions. Everything with nitrate and sodium is soluble. Sulfate has the couple of exceptions as well. Barium, lead, and calcium. So again, as you practice these, you learn to get a little bit quicker at it. And then last thing I want to say is if it doesn't appear on the list, this is probably where you want to use process of elimination. So if it doesn't appear on there, so like dichromate doesn't appear on there, acetate doesn't appear on there, there's lots of ones don't appear on this list. If you don't have the polyatomic ion that you're looking for, look at the other one, right? See if that one's on there. And if the other one's on there, you might be able to eliminate one of your two options. And if you have both of them that aren't on there, then chances are pretty good. If none of these rules apply, those are probably precipitates, just so you know. Okay, there you go. How to use solubility rules. We're going to put it all together in the next step, how to write these equations and then how to predict what our products are going to be. So I will see you in the next one. Solubility rules, we're all done. Have a good night.